All right. This lecture will cover section 2.8 about uh, probability distributions other than the binomial and normal distributions, which we've already covered in sections 2.6 and 2.7 respectively. These distributions they're not going to come up as much in this course, okay? But I just wanted to give you some exposure to some other kinds of distributions that you could encounter. So an example of another discrete distribution besides the binomial would be the Poisson. So a Poisson distribution is a type of discrete variable. If x is a random variable that counts the number of occurrences or successes of an event within a specified interval, then x is said to be a Poisson random variable. More formally, x follows a Poisson process if the three conditions below are met, right? And I won't take the time to read through those to you, but just to give a couple examples, the number of accidents at a given intersection in a week would be a Poisson random variable, or the number of beetles within an enclosed area of 1,000 square feet, right, would also follow a Poisson distribution, or could anyway. So the way that the Poisson distribution works is if x is a Poisson random variable, then the probability of obtaining x successes in an interval of fixed length t is given by this probability density function. The Greek letter lambda here represents the average number of successes in an interval of length 1. And the number e here is approximately 2.7. We'll use a calculator, of course, and if you're using a scientific calculator, then e will already be programmed in, right? The mean, or in other words, the expected value of a Poisson random variable is lambda times t, which makes sense because lambda is the average number of successes in an interval of length 1, and t is the length of the interval that we're interested in. So the expected number of successes within a particular interval would be lambda times t. Okay, the number of successes in an interval of length 1 times the length of the interval, right? So that's the idea. And then the standard deviation of a Poisson random variable is just the square root of the mean, which is an interesting thing about Poisson variables. I haven't provided any links to proofs of these facts, but we will practice applying them. Okay, so let's take a look. Number 1 here says cars arrive at a particular McDonald's drive-thru at the average rate of 0.2 cars per minute between the hours of 3 p.m. and 4 p.m. Let x be the number of cars that arrive in any given 20-minute interval of time between 3 p.m. and 4 p.m. Part A asks us to compute the probability that x equals 5, so that 5 cars arrive between 3 and 4 p.m. So we will use the Poisson distribution to calculate this probability. And in order to use the Poisson distribution in Desmos, all we need to do is identify what the mean is. In this case, so we're going to use the Poisson dist. Actually, you need a everything should be lowercase. So we should have Poisson dist, and then we'll put the mean in. In this case, lambda is 0.2, right? 0.2 cars arrive every minute, and t is 20, right? So mu, right? So just doing a little bit of scratch work, mu for our random variable x would be lambda times t. That's 0.2 times 20, which is 4. Okay, so we'll use the Poisson distribution with a mean of 4. And then for our minimum value, we'll put 5, For our maximum value, we'll put 5. And then we'll be able to compute probability that x equals 5. So let's take a look. Okay, so in Desmos, we'll type in Poisson Dist. Okay, and then it becomes normal faced. And we have a mean of 4 in this case. I'm going to go ahead and zoom in by clicking on that little plus sign magnifying glass thing, and then I'm going to click on Find Cumulative Probability. I want the probability that x equals 5, so I'm going to put 5 for my lower bound, 5 for my upper bound, and you can see that it's giving me that bar representing 5. The probability that we have exactly 5 cars show up in a 20-minute interval between, 3 and 4 p.m. is 0.1563, so 15.63% chance, 0.1563. Okay. Part B says to compute mu sub x. Well, we had to do that to do part A, right? Mu sub x was lambda times t, which was 0.2 times 20, which came out to 4. And then we're asked how many cars would you expect to arrive between 3 and 3:20 p.m., and we would say we would expect 4 cars. We're not guaranteed that exactly 4 cars will show up. For example, there's a little over 15% chance that 5 cars will show up. But we expect 4 because that's the mean. Okay, and then part C asks us to compute the standard deviation. Well, the standard deviation of x would be the square root of lambda times t, right? Well, we already know that lambda times t is 4 because that's what we did in part B, so this is just the square root of 4, which you could use a calculator for if you don't know. But it is just 2. So that's it for number 1. That's how Poisson distributions work. Let's look at another type of distribution. So the uniform distribution is an example of a continuous distribution. Okay, so a random variable x is uniform if x can take on any value between some lower limit a and some upper limit b, and 2, the probability that x is in any particular interval is equal to the probability that x is in any other interval of equal length. Here is the PDF for a uniform random variable. This is the mean of a uniform variable, and this is the standard deviation of a uniform variable. Let's practice using these distributions. Again, don't freak out about this function looking crazy because we're just going to use Desmos, okay? We'll use the uniform distribution in Desmos. So number 2 here says cars arrive at a particular McDonald's drive-thru at the average rate of 0.2 cars per minute between the hours of 3 and 4 p.m. Oh, this sounds familiar, right? So in other words, on average, a car arrives at the drive-thru about once every 5 minutes. Okay, a car arrives at the drive-thru at a time x that is uniformly distributed between 3 and 3:05 p.m. Part A says, find the probability that the car arrives between 3:01 and 3:03 p.m. Okay, so we'll use the uniform distribution for this. And to use the uniform distribution in Desmos, first of all, I'm just going to click that little graph button so that the Poisson goes away. I might bring it back if I need it later. But to use the uniform distribution, we just type uniform dist, okay? And then you put in the lower bound and the upper bound of your distribution. In our case, we're told that cars arrive at the drive-thru at a time that's uniformly distributed between 3 and 3:05 p.m. So what I'm going to do is I'm just going to set 3 o'clock p.m. as 0 and 3:05 p.m. as 5 since it's 5 minutes later. So I'm going to set my lower bound at 0 and my upper bound at 5, okay? So let's go back and put in 0, 5. Okay, and I can click the little magnifying glass again to zoom in. So there you go, it's drawing this uniform distribution. It's a very strange distribution, but this is the way it's supposed to look. And now we want to find a probability. We want to find the probability that x is between 301 and 303. Well, if 3 o'clock is our starting point 0, then 301 would correspond to 1, and 303 would correspond to 3. So in other words, we're looking for the probability that x is between 1 and 3. And we used the uniform distribution with 0 as our lower bound, 5 as our upper bound. The minimum for the probability that we want to compute is 1, and the maximum for the probability we want to compute is 3. So we'll go put those in. 1 and 3. And there you go. And you can see that it's shading in the region representing 1 to 3, right? 1 to 3. And it looks like there's a 0.4, the 40% chance of this occurring. Okay. Part B says compute mu sub x. What time would you expect the car to arrive at the drive-thru? Okay, so mu sub x. We were told that the mean is equal to a plus b over 2, right? So in our case, a is 0, b is 5. So we have 0 plus 5 over 2. And that comes out to 2.5. You can punch that into your calculator, but that would be the answer. So what time do you expect the car to arrive at the drive-thru? We would say we expect the car to arrive 2.5 minutes after 3 p.m. Right, that is at 3:02 and 30 seconds, right? p.m. Okay, so that's the mean. Standard deviation. Okay, part C asks us for the standard deviation. This is the square root of b minus a squared over 12. In our case, b is 5, a is 0. Five minus 0 is 5, and 5 squared is 25. So this would be the square root of 25 over 12. I'm going to have to use the Desmos calculator for this. Square root of, let me use the scientific calculator, square root of 25 over 12 is about 1.44. So mean and standard deviation. Okay, the last two examples, the one with the Poisson distribution and the other one with the uniform distribution, were pretty similar. They're both talking about cars arriving at a drive-thru. But notice that number 1 is talking about the number of cars that arrive in a particular time interval. And number 2 is talking about the time that they arrive. Notice that number 1 is discrete, therefore, because you're counting up the number of cars that arrive. Whereas number 2 is continuous, because you measure time, right? Time is a continuous variable. In general, if you're thinking that Poisson variables and uniform variables are very similar, you're on the right track. You might say that the Poisson distribution is the discrete version of the uniform distribution, which is continuous, okay? In general, for a Poisson process, if only one event occurs in the interval between 0 and t, Then the number of occurrences is a Poisson random variable, and the timing of the occurrences is a uniform random variable. That's not something that you're going to be tested on or anything like that. It's just for your information. If you were thinking, wow, like, wait, what is the difference between these things? Well, that's the difference, right? That's the difference. Okay, there are other kinds of variables. They start to get very complicated in terms of their probability density functions. We could talk about more simple probability density functions, but the reason I list students' t-distribution here is because students' t-distribution is one that we will use later on in the semester in order to do certain hypothesis tests and confidence intervals. It's a complicated distribution mathematically. Geometrically, if you look at a graph of this thing, it looks bell-shaped like the normal distribution. And as your sample size n gets larger, it basically becomes the normal distribution. So as n gets large, this turns into the normal distribution. We're not going to use this function, and so we're not going to manipulate it directly, right? We'll just be using the Desmos calculator, so you don't need to worry about it too much. This is the mean and standard deviation of the distribution. The mean of the t-distribution is always 0, right? It's just always 0. And then the standard deviation of the t-distribution will be the sample size divided by the sample size minus 2, which is kind of interesting. It's common to describe the t-distribution in terms of degrees of freedom, or df for short. Different distributions will have different degrees of freedom. For students' t-distribution, the number of degrees of freedom is always sample size minus 1. So if you have a sample size of 40, then you have 39 degrees of freedom. If you have a sample size of 112, then you have 111 degrees of freedom, okay, for students' t-distribution. When we use students' t-distribution in Desmos, we'll have to put in the degrees of freedom, okay? So number 3 asks us to compute a t-distribution, or a t probability. It says, suppose that t follows students' t-distribution with 12 degrees of freedom. Compute probability that t is greater than 2. So in Desmos, this one's really simple. We just call it t-dist. And then we put in the degrees of freedom, which in our case is 12. We still have to put in a minimum value for the probability we want to compute. We're looking for the probability that t is greater than 2. So the minimum will be 2. The t-distribution, by the way, is continuous. So we'll put in minimum is 2. Maximum is infinity. And then we'll look for the probability that t is greater than 2. Let's take a look in Desmos. Let me hide that one. And here I want to do t-dist with 12 degrees of freedom. And let me get a good zoom on it. So there's the t-distribution. We want to find a probability, so I'm going to click that button. And what probability are we looking for? 2, greater than 2. Whoops. 2. Where did I go? Here I am. So 2, no maximum. So you can see it's highlighting the right thing. And that probability is about 0.0343. Okay, so that example was kind of boring because we didn't really have any situation. We're basically just crunching numbers with no context for what these numbers mean. Unfortunately, that's just kind of that's just kind of how we'll have to handle students' t-distribution for now, because we need a little bit more information to understand why we need students' t-distribution, and that information will come later in the course. I just wanted to mention it because there are going to be other distributions that are similar to that, right? The chi-square distribution, the F distribution. These are distributions that will come up later on in the course. And I'm not going to introduce them to you at this time, because just like the t-distribution, their usefulness is kind of difficult to describe without a little bit more context. But that kind of will get our feet wet at least. And in addition to these distributions, of course, there are other distributions that we're not going to see. You could spend a lot of time diving deeply into probability. I took 2 courses in just probability while I was getting my degree, right? I took 2 courses in just probability, and that even wasn't, that was just barely scratching the surface. So anyway, this is all that we'll say about distributions. If you're interested, you could take a look at this link. It's interesting. It lists off all of these probability distributions and the relationships between them, because a lot of these things are related in a similar kind of way that the uniform and the Poisson distributions are related, right? There's all kinds of relationships between these various probability distributions, and this is a really interesting chart to take a look at if you're interested. But that's all I have to say about these other kinds of distributions for now. I'll be honest, this isn't going to be a major focus of the course, so you don't need to stress out about this too much. But just know that there are other kinds of probability distributions out there. We're going to be focusing mainly on the binomial and on the normal. So that's all I have to say about that, and I will check in with you in the next section.